The South China Sea at 2:11 a.m. in April carries the quiet of deep water far from land. The Spratly Archipelago is 140 nautical miles to the northwest, and in that direction, the sea is shallow, contested, and crowded with the infrastructure of a territorial dispute that has been generating international incident reports for a decade. But here, in the passage between the Spratlys and the Philippine coast, the water is 3,400 meters deep, and the nearest feature is the distant glow of a Filipino fishing fleet working the shelf edge to the east. USS Fitzgerald makes 20 knots on a westerly heading, 210 nautical miles from the nearest port of call, 340 nautical miles from Subic Bay, conducting a freedom of navigation operation through the western Philippine Sea approach to the contested features. She has been at general quarters for 12 minutes. Ever since the combat systems officer classified the YJ-18 battery activation on a Chinese surface combatant 80 nautical miles to the northwest. Not a launch, not a targeting event, but an active radar mode consistent with pre-engagement preparation and one that the commanding officer has decided deserves a precautionary GQ. The YJ-18 launches at 2:13:41 a.m. The intercept is clean. SM-2 at 28 miles, proximity detonation. The YJ-18's guidance system disabled. The terminal sprint phase never initiated. What remains of the YJ-18 at the point of intercept is a fragmenting airframe moving at approximately Mach 1.7 on a descending trajectory. The Fitzgerald's second SM-2, assigned as insurance, fires 7 seconds after the first. It arrives at the fragmenting debris field at 2:14:28 a.m. and achieves a secondary detonation that disperses the larger fragments. The debris field that reaches the Fitzgerald's vicinity at 2:14:43 a.m. is widely distributed. Fragments ranging from 0.3 kilograms to 12 kilograms, spread across approximately 350 meters of cross-track distance. Most of the fragments impact the water around the Fitzgerald. One impacts the ship. The impacting fragment is the YJ-18's forward fuel tank structural section, approximately 22 kilograms of aluminum alloy framing. At the point of impact, it is moving at approximately Mach 0.9. It strikes the Fitzgerald's hull plating at frame 48, port side, at approximately 0.3 meters above the waterline. The geometry, 22 kilograms at Mach 0.9, striking a curved hull plate supported by the frame structure, produces a specific result. The hull plate at frame 48 does not breach. The 19mm HY-80 steel resists penetration, but the kinetic energy of the impact does not disappear. It distributes. The impact energy transmits into the hull structure as a high-frequency stress wave, a mechanical impulse that propagates outward from the impact point in all directions through the ship's structural steel. Not enough to break frames, not enough to rupture piping or fracture major structural members, but sufficient at its propagation distances to impose stress on the weld seams that join the hull plating sections to each other and to the internal frames and stringers. Weld seams are the structural joints of a warship's hull, places where two steel sections are fused together by the welding process into a connection that is, in theory, as strong as the parent metal. In practice, weld seams accumulate micro defects over a ship's service life. Incomplete fusion in local areas, porosity from gas bubbles trapped during welding, residual stresses from the thermal cycle of the original welding. These defects are assessed and accepted within design tolerances during construction and at maintenance intervals. A weld seam with micro defects within tolerance is not a failed weld. It is a normal weld in service on a ship that has been operating for years. The stress wave from the 22-kilogram impact at frame 48 reaches these micro defects in the weld seams of the Fitzgerald's hull in the zone between frames 40 and 56. In 11 separate weld seams in this zone, the micro defects propagate. Not to full-length cracks, not to structural failures, but to short through-thickness cracks that penetrate the full 19mm thickness of the hull plating at weld seam locations, connecting the ship's interior to the sea at specific points along the weld lines. Each crack is between 2.5 and 7 centimeters long. Each is open to the seawater pressure of 0.3 meters of head, sufficient to drive seawater through a 2.5 centimeter crack at a measurable flow rate. The 11 cracks open at 2:14:43 a.m. The Fitzgerald has no hull breach. She has no flooding alarm. What she has is 11 points in the hull between frames 40 and 56, each admitting a thin stream of seawater into the ship's interior spaces at rates between 15 and 40 milliliters per minute per crack. The combined inflow rate from all 11 cracks is approximately 340 milliliters per minute. The Fitzgerald's bilge monitoring system operates on sensors that detect when the bilge water level in a given space rises above a threshold of approximately 4 centimeters of standing water. The 11 cracks are in 7 different compartments between frames 40 and 56. The forward engineering passageways, the auxiliary machinery space, the forward pump room, the forward berthing spaces adjacent to the hull, and the combined inflow to any single compartment from its 1 or 2 cracks is between 15 and 80 milliliters per minute. None of these individual inflow rates will fill any single compartment above the bilge alarm threshold in under 4 hours. None of them will trigger an alarm in the next 60 minutes. But they are all open simultaneously, and the ship is 3,400 meters above the South China Sea floor and 210 nautical miles from the nearest support. The flooding watch petty officer in DC Central does not notice anything at 2:14:43 a.m. because there is nothing to notice. The bilge alarm status board shows all green. The ship's list indicator shows 0.2 degrees port, normal operating range. The damage control status display shows no active flooding anywhere on the ship. The post-debris impact assessment has been completed. Hull intact, no penetration detected. Damage assessment team topside reports 1 impact mark on the hull plating at frame 48 with no breach. The commanding officer is informed at 2:16 a.m. that the ship is undamaged. The ship reduces to modified readiness at 2:17 a.m. The water continues coming in. At 2:44 a.m., 30 minutes after the impact, the bilge pump in the forward pump room cycles on for the first time that watch period. This is not an alarm event. Bilge pumps cycle on and off routinely in response to accumulated bilge water from normal condensation, equipment drips, and minor moisture ingress. The forward pump room bilge pump cycling at 2:44 a.m. is noted in the bilge pump log as a routine cycling event. The pumping cycle lasts 4 minutes and removes approximately 19 liters from the forward pump room bilge. This is slightly more than the typical condensation accumulation for a 30-minute period in the South China Sea humidity. But within the range of variation, a watch stander would attribute to higher humidity on a warm night. At 3:02 a.m., the auxiliary machinery space bilge pump cycles on. Also routine. Cycle duration, 6 minutes. Removed, approximately 28 liters. Bilge pump log notes, routine cycling. The watch stander does not cross-reference the auxiliary machinery space cycling with the forward pump room cycling 20 minutes earlier. At 3:19 a.m., the forward pump room bilge pump cycles on again, the second time in 35 minutes, where the normal interval for this space is 60 to 90 minutes. The watch stander notes in the bilge log, cycling more frequently, possibly high humidity or minor condensation increase. Monitor. Still no alarm. The bilge level at the cycle trigger point was 4.8 centimeters, 0.8 centimeters above the normal cycling threshold, but below the 8 centimeter alarm threshold. At 3:31 a.m., the chief engineer is conducting his engineering log review when he reads the bilge pump log for the past hour. He reads, forward pump room cycling at 2:44 a.m. and 3:19 a.m. Auxiliary machinery space cycling at 3:02 a.m. 3 spaces in the same general zone of the ship cycling in the same watch period. A pattern that does not appear in his typical log review. He notes it and continues his review, moving up to DC Central at 3:32 a.m. At 3:41 a.m., the forward berthing space bilge alarm activates. The bilge level in the forward berthing space, the crew sleeping quarters immediately adjacent to frames 44 to 48, has reached the 8-centimeter alarm threshold. The berthing space bilge pump, which has been running for the past 19 minutes, is not keeping up with the inflow. At 3:41:04 a.m., the chief engineer reads the bilge alarm for the forward berthing space and makes the connection. 4 separate spaces between frames 40 and 56 are accumulating bilge water faster than normal, all within the past hour, all since the debris impact at 2:14 a.m. He does not immediately know what is causing the inflow. He knows where to look. He calls the repair party for Zone 2. I need an immediate inspection of all hull weld seams in the frame 40 to 56 zone, both sides, at or near the waterline. I am specifically looking for hairline cracks in weld seams at or below the current waterline. Take a flashlight and a mirror. Run your hand along every horizontal weld seam at the turn of the bilge and report any seeping, any moisture, any corrosion tracks from moisture. The repair party begins its inspection at 3:43 a.m. 12 personnel, both sides of the ship, crawling through the bilge spaces and the lower hull accesses in the frame 40 to 56 zone. They are looking for something individually very small. A 2.5 to 7 centimeter crack in a weld seam, weeping water at less than half a teaspoon per second. In the bilge spaces, which are dark, warm, and occupied by piping and structural members, a crack of this size can look like a corrosion track or a grease smear. The first crack is found at 3:47 a.m. in the forward pump room, port side, at the weld seam between the hull plate at frame 44 and the bilge keel stringer. The repair party leader reports, "Chief, I have a weld seam crack. Port side frame 44, approximately 3 centimeters. Water seeping at the joint. Definitely active inflow." The chief engineer responds, "Mark it. Continue the inspection. I need the full picture before we start any repair." The inspection continues. Crack 2 at 3:49 a.m. Starboard side, frame 47, approximately 4 centimeters. Crack 3 at 3:51 a.m. Port side, frame 43, 2.5 centimeters. Crack 4 at 3:52 a.m. Port side, frame 51, approximately 6 centimeters. The most active crack found so far with a visible trickle running down the hull face. Crack 5 at 3:54 a.m. Starboard side, frame 53, approximately 5 centimeters. Crack 6 at 3:56 a.m. Port side, frame 46, 3.5 centimeters. Crack 7 at 3:57 a.m. Port side, frame 49, 7 centimeters, the longest found. By 4:01 a.m., the inspection has found 9 cracks. By 4:07 a.m., it has found 11. All 11 cracks are in the zone between frames 40 and 56. All 11 are at weld seams. All 11 are actively admitting water. The chief engineer has the complete picture at 4:08 a.m., 53 minutes and 25 seconds after the debris impact. He has been managing the flooding picture while the inspection ran. Additional bilge pumps brought online in the affected spaces. Bilge alarm thresholds temporarily lowered, so accumulations of 3 centimeters trigger cycling rather than 4 centimeters. Dewatering priority assigned to the forward pump room and forward berthing spaces where inflow rates are highest. The ship's current flooding status: 7 compartments between frames 40 and 56, receiving water through 11 cracks at a combined rate of approximately 340 milliliters per minute. The bilge systems in those spaces removing water at approximately 280 milliliters per minute. A net inflow of approximately 60 milliliters per minute across the zone. The ship is flooding slowly across a distributed area. and the flooding rate is currently exceeding the dewatering rate by a persistent margin. His problem is the repair approach. A single large hull breach can be addressed with concentrated resources. 11 small cracks distributed across 7 compartments require 11 separate repairs conducted simultaneously, because if only some cracks are repaired, the remaining ones continue to accumulate, and the dewatering system still cannot keep up. He needs 11 repair teams working simultaneously. He has the personnel. What he does not have is unlimited materials. Hydraulic cement, which sets in wet conditions and is the ideal material for sealing an active water-admitting weld crack, is available in 4 2-kilogram cans in the damage control stores. 4 cans for 11 cracks. He inventories the alternatives. The DC locker system carries hydraulic cement, 4 cans, underwater epoxy putty, 6 2-part cartridges, rubber sheet material with C-clamp assemblies, 8 sets, fiberglass repair cloth with marine epoxy, 3 kits, and wooden plug sets, 11 cracks. He allocates hydraulic cement for the 4 largest active cracks where the water flow requires the setting in wet capability. The 7-centimeter crack at frame 49, the 6-centimeter crack at frame 51, the 5-centimeter crack at frame 53, and the 4-centimeter crack at frame 47. Underwater epoxy for the next 4 mid-size cracks. Rubber sheet patches with C-clamp harness assemblies for the 3 remaining cracks at locations with structural access for the clamp attachment points. He briefs the 11 repair teams at 4:11 a.m., assigning each team to a specific crack with specific materials and a specific method. He specifies the sequence. Hydraulic cement teams first, because their material requires the most working time. Epoxy teams second. Rubber patch teams in parallel with the epoxy teams because their method does not interfere. The 11 teams begin their repairs at 4:14 a.m. The spaces they are working in are the bilge accesses of a warship. Dark, narrow, limited working clearance at the weld seam locations. Warm from the South China Sea ambient temperature, with active water inflow making the work surfaces wet. The hydraulic cement teams work fastest. The team at frame 49, the longest and most active crack, applies a full 500-gram portion of hydraulic cement across the 7-centimeter crack face at 4:16 a.m. The flow from that crack reduces to a seep within 40 seconds as the cement begins blocking the crack width. The underwater epoxy teams are mixing their 2-part cartridges through static mixing tips that combine the components as they exit. The resulting compound applied directly to the crack face and surrounding metal, forming a flexible adhesive patch that cures in the wet environment. Working time after mixing, approximately 8 minutes. Full cure, 45 minutes. The teams at frames 46 and 44 apply their epoxy patches at 4:17 and 4:18 a.m. respectively. The rubber patch teams work with 30-centimeter square rubber sheets, fitted with threaded stud attachments at the corners. The studs pass through C-clamp assemblies that grip the surrounding structural members and pull the rubber sheet tight against the hull face over the crack. The patch reduces the flow through the crack by increasing resistance to flow at 15 to 25 milliliters per minute inflow, sufficient to drop each crack's contribution below the bilge pump's management capacity. The rubber patch teams complete their 3 patches at 4:19, 4:21, and 4:23 a.m. The hydraulic cement team at frame 49 reports initial set complete at 4:19 a.m. The trickle from that crack has reduced to approximately 2 milliliters per minute. The 3 other hydraulic cement applications are progressing similarly. At 4:22 a.m., all 4 hydraulic cement applications have achieved initial set, and the cracks they cover are no longer contributing meaningful inflow. By 4:31 a.m., all 11 repair applications are complete. The chief engineer calls for a system status update at 4:35 a.m. Bilge pump cycling rates in all 7 affected compartments, all reported within normal condensation ranges. Net inflow across the zone. approximately 18 milliliters per minute. Below the combined bilge pump capacity, meaning the affected spaces are now dewatering rather than accumulating. He posts a flooding rewatch at each of the 11 repair sites, with instructions to monitor for any failure of the repair materials or any new seeping at adjacent weld seams stressed by the same impulse but not cracked during the initial inspection. The rewatch teams check their assigned sites every 15 minutes for 2 hours. At 6:44 a.m., 4 hours and 30 minutes after the debris impact. The 2-hour rewatch period completes. All 11 repair sites are holding. No new cracks have been identified in adjacent weld seams. The flooding in all 7 compartments is trending toward pre-impact baselines as the bilge pumps remove the accumulated water from the undetected seepage period. The Fitzgerald continues her transit. The 11 temporary repairs hold until Subic Bay, where the ship undergoes a full weld seam inspection of the frame 40 to 56 zone and permanent weld repair of all 11 crack locations. The yard assessment requires 72 hours of welding work, and the assessment also identifies 3 additional micro defects in adjacent weld seams that did not propagate to through thickness cracks under the stress wave, but show crack initiation features. They are repaired preventively. The post-event engineering review identified the detection gap as the primary concern. The ship was flooding from 11 simultaneous sources for 53 minutes before the pattern was recognized. The bilge monitoring system, designed to detect individual compartment flooding events, had no mechanism to aggregate cycling rates across multiple compartments into a pattern alert. Each individual cycling event was below the threshold that would flag it as anomalous. Only the human pattern recognition of the chief engineer, reading 3 cycling events in one zone during his routine log review, caught the aggregated picture before it became a genuine flooding emergency. The review recommended a zonal bilge cycling frequency monitoring function added to the DC Central Display System, a software modification that would flag when 3 or more bilge pumps in a defined hull zone cycle within the same 15-minute window, regardless of individual alarm status. The modification was assessed as straightforward to implement. It was scheduled for the next software update cycle. The chief engineer was asked, at the debrief, what would have happened if he had not read 3 cycling events in his log review at 3:31 a.m. He said the bilge alarm in the forward berthing space would have activated at 3:41 a.m. regardless, and that alarm would have triggered an investigation. He said the question is whether the investigation would have connected the berthing space alarm to the pump room and machinery space cycling events from earlier in the watch. Whether it would have looked for a distributed cause rather than a single space cause. He said he did not know. He said the distributed nature of the flooding made it look like several small, unrelated events rather than one large connected event, and that a single space-focused investigation might have missed the connection. He paused. Then he said, 11 small cracks. Each one is below the threshold of concern. Each one looks like normal ship moisture. Together, they are a flooding event. He said the ship's system was designed to find one large problem. He said reality sometimes sends 11 small ones instead. One Norwegian 18 structural fragment, 22 kilograms, impacted the hull at frame 48 at Mach 0.9 at 2:14:43 a.m. Hull plating, no breach. Stress wave propagation across frames 40 to 56 caused propagation of micro defects in 11 weld seams to through thickness cracks. Combined inflow rate, approximately 340 milliliters per minute across 11 cracks in 7 compartments. No individual crack reached the flooding alarm threshold. Pattern recognized by Chief Engineer at 3:31 a.m. from bilge pump cycling frequency in log review. Bilge alarm for forward berthing space activated at 3:41 a.m. All 11 cracks located by inspection at 4:08 a.m. Elapsed time from impact to full damage picture, 53 minutes and 25 seconds. 11 simultaneous repair teams deployed at 4:14 a.m. using hydraulic cement, underwater epoxy, and rubber patch assemblies. All 11 repairs complete at 4:31 a.m. Net inflow reduced to 18 milliliters per minute. Below combined bilge capacity. Rewatch period completed without incident at 6:44 a.m. Ship status operational. 11 cracks. None of them were a crisis. Together, they were one. The chief engineer read a log. 3 cycling events. Same zone, same hour. That was the whole alarm. Not a siren, not a flashing panel, not a voice reporting emergency flooding. 3 entries in a bilge pump log that he read because reading the bilge pump log is part of his job. The ship was saved, if saving is even the right word for what happened here. Not by a dramatic repair under impossible conditions, but by the quiet discipline of reading everything and noticing when something is slightly off. The water came in slowly, 11 ways at once. The answer came the same way. 11 teams, 11 repairs, all at the same time. The log still shows the 3 entries. They always will.